Let me record to this computer and then okay. So yes, I was saying just to go briefly over like the syllabus. Let's see. Okay, so those are my as I was saying, like my email. You can also come here if you need it. Those are my like office hours for the time being. Like they could change, and like once we're closer to like exam weeks and things like that, I'll give you more office hours. So like don't take that too seriously, but like I just have to put like a particular time of the week. But again, like I'll probably like as like the course progresses, like I'll like add some more. Also, we will have like a kind of like a TA. We don't have recitations, but we do have a kind of like a TA who will have like office hours. He will send you like an email with those as well. Um, so like so the requisite is like linear algebra. And that is something we'll definitely use a lot in terms of like of the textbook. So um, if you go to the department, the math department side, they kind of like have like a recommended book for this course, but that book is kind of like interesting for a mathematician. I don't know if it's like interesting for a non-mathematician, so that's why I'm not using it as the official one. It's still kind of like like again, like it does mention many cool things, but it just has like 3 or 4 chapters on this topic. So in fact, like just some terminology. So I'll usually refer to like the course as linear optimization. Like it may also go under like linear programming. That's kind of like another name for like a typical name for like these topics that we will cover. Um, so the programming thing, the word, like kind of like fun historical fact, it is not per se related to computer science. It's just like the army. I don't know if it's kind of like standard terminology that they keep using. It's just like the army would refer to like a program as like say when you're allocating resources or things like that, they would call that like a program. So it comes actually has more like military origins than computer science origins, despite the fact of the word programming. But of course, like now, if this is like really useful for computer science or like for like applied, like it's kind of probably one of the more applied courses that you will take at like at the university. So like now it is related to computers, but like originally it had nothing to do with computers. So yeah, I think I have like a quick PDF that mentions some of like, the history because it's kind of like fun, like how it kind of developed and because it was during like World War II and then the Cold War. So there was like this competition with the Soviet Union. So it kind of was weird because some things were developed in the Soviet Union, but they couldn't use like the word prices because they were communists. So everything had to be kind of like written in a very weird way to get like approval from like the like whoever was in charge of like running like mathematics in the Soviet Union. So I mean, they're kind of like historical things that are kind of like actually interesting to learn about. But anyway, so linear optimization, I feel is kind of like gives you like a better sense of what the course is about. Um, so what I was saying is that the textbook that's on the department website kind of like goes into many other things that are not related to linear optimization. So as the official textbook, I put this one, which what I like is because like the editorial, I don't know if I mentioned it here, but it is like from a Springer textbook, and Rutgers students like have like access to most of the Springer textbooks for free, so you can just download it from the university libraries. Let me see if this link actually works. Um, what happened? I mean, I kind of tried to put like a link here. I don't know if it's like, oh, maybe it's not opening. Well, it does have like a massive link here, but like, let me just show you how, if you wanted to find it, you could just go to Rutgers libraries, like, and then like enter the name of the textbook. So understanding and using linear programming. And there you find it. So I think, yeah, even undergraduates should have like access to all these books for free. And I don't think it's just like because I'm faculty. So that's kind of what I like. It's still like probably there's a couple of things that may need to be complemented, but then I'll just kind of like make something else available. I won't kind of like follow too closely like the textbook, but it is actually like a pretty good book. And if you like, I do recommend it. Like, and I will kind of like give you like a sense of when I cover something roughly to what sections it corresponds to the book. But it does kind of give like useful insights. And it does mention some more technical things. Again, if someone is interested in more like the implementation part of this, like, okay, so like how efficient is it? Like algorithm, like, more like computer science stuff, like, which are kind of like practical things that you would really actually need to understand if you want to use this in practice, because if you ever use this in practice, it would be a gigantic problem that you need to run on a computer, right? Like you would never do anything of what we'll learn by pen and pencil. No one ever uses that. Like that's kind of like over these days. So, but anyway, so like again, like if something else is needed, I'll like make it available. And then in terms of like topics, well, like as I said, I'll give you like a more like of an introduction to the course in a bit. Maybe like in terms of like the structure of the course, since we don't have recitations, like we will have like 3 exams throughout the semester plus the final like I still don't have the date, so that it will happen somewhere like around here or maybe the week after. So yeah, there will be some like assignments that I'll give you, but like most of the percentage like of the grade will go to is distributed among the exam. So at least the way I'll do it is like break it, like compute the way in the grade in 2 different ways. Like the track one, which is what I'm calling this, is just one where like the midterms, if you like, are weighted a little bit more, and track 2 weights more the final. So whichever is most ends up giving you a better grade, that's the one that you will get at the end of the semester. Like this is kind of like to reward more, sometimes like for the final, like if you put like an extra effort, like you can kind of like do really well, and that should be like rewarded more. So like, like then you could just like get this one applied to you. But again, you will get like the highest of the two. And then like there's like kind of like some, preliminary grade cutoffs. So I don't know if I can see. And now this is where you can see all of that. So again, it's kind of like, okay, so if you get like a 72% but based on whatever like the max of those 2 grades is, then you're guaranteed a B. That could end up being lowered, like, it could start at 70 or whatever. That would be determined more like based on how everyone is doing. But at least like it wouldn't go higher than this, right? So like at least if you have like a 72, for example, you would be guaranteed a B. But like again, like the B or all these other grades could start a bit lower, and like we'll see how like the semester goes, to determine that. But yeah, like that's kind of like at least in terms of like the structure of the course, like of like the grade and all that stuff, like what I had in mind. I don't know if there are any questions about this. So good. Okay, so. And as I was saying, I will record like the classes. So like after each class, I'll kind of like send you the link to the video if you want to watch it. I did create like an assignment, a poll. Okay, sorry, this is like a different class. Why am I opening? What happened with the optimization class? I thought we were fine. Where did it go? This is Calcutta. Where could here you are. So I did create a poll, which is optional, but it's kind of like useful. There's like just some brief questions. If you have taken multivariable, like not that it will be needed, but it is actually, it kind of like it's a course that does interact well with this class. I already saw from some of like the responses, like not everyone plans on taking it or anything like that, so it's totally fine. But I may like at least maybe like as an extra thing, like I may want to mention something about that. So for those who have taken it, like that could like I may throw in some like like small things that like from time to time just to like connect the ideas. Then what other courses you're taking, if this is like the last math class that you're taking here at Rutgers, and what are you trying to major in and things like that. So like, based on like the distribution of like interest, because I don't think I said it, but probably we kind of will have like at least 2 or 3 weeks at the end of the course of applications. So there are tons of applications for linear optimization. So like it does make sense to kind of like try to find applications that fit the best to, like the interests of the class. So like if you answer this, like that kind of gives me like a better sense of what I should like aim for. But I like, yeah, like the easiest way to summarize this course is like, what is linear algebra? Let's go to 250. What is linear algebra? It's matrices and Gauss-Jordan elimination over and over and over and over and over. Like everything can kind of be done like through a Gauss-Jordan thing. Like, if you kind of remember like that class. What is linear optimization? At least like the way we will approach it, it is matrices also, but instead of like something called Gauss-Jordan, like it's something called the simplex method. So that's kind of like will be the analog of this, like, the kind of like the closest thing that every single problem will involve in some way or another will be the simplex method here. And again, in linear, in like 250 in linear algebra, it was like Gauss-Jordan elimination, like row operations and all that stuff. But so it's really similar in the sense like, there's not that many techniques to learn. You just have to learn one thing really well, and then you apply it like crazy to everything. Like, so that's why there's kind of like opportunities to kind of like branch out in different like applications depending on what people like. So like, yeah, if you want to reply to the poll, then that will give me a better idea. But again, it's like not something that has to be decided right now. It's like interest might change over time, but at least it does give me something to keep in mind as I prepare like kind of like where like the trajectory of the course. Okay, so I'm going to kind of like give you for today just like an idea of like, what are the basics behind linear optimization, and so I'm actually there are a couple like important things that you can kind of like see already like in a simple example. So let me see if I can do that. And also like, as I write the notes, I'll share them with you as well. After like once I send you the link for the video. Let's see. Okay, so I'll start with the most basic problem you could ever think of about this. Um, it's so basic that you don't need almost any knowledge to solve it. Like you'll see. Uh, but it is nice because it allows you to draw everything, which is not something we will do like 99% of the time. So sometimes this is called like kind of like the farmer's problem. So like I'll make it like super simple. So let's say you have two types of seeds, like uh I don't know, potato seeds, carrot seeds. So let's say you have like 3 tons of potato seeds, 4 tons of carrot seeds. And then you have fertilizer. So you want to grow the seeds. So let's say you have like 5 tons of fertilizer. And you kind of like assume that it's like a 1-to-1 ratio. Like say if you wanted to grow 1 ton of carrot seeds, then you would need like a corresponding ton of fertilizer just to make the number simple. Of course, like there could be more interesting relations between them. Okay. But if you grow like potatoes or carrots, like you will be paid like a certain amount of money. So let's say just to make some like simple numbers that you're going to get paid, you know. So for each like kilogram of potatoes, you get paid $1.2, and for each kilogram of carrots, you get paid like $1.7. Okay. Of course, like these numbers are very simple, just like so that we can keep track of them like without much thought. But like, it's kind of like easy to think about how this could be generalized, because then you could have like tens like of different seeds, 20 or 30 different seeds that you could grow, and they get priced at different cost. Like, they could be sold at different costs, but then maybe there's like a shipping cost, like when you have to send it to a supermarket, and like you kind of like keep adding like difficulty to the problem, and you can make it more complex, right? But like, like this is like a what you would call like a like a baby example, right? And so like, kind of like the word optimization kind of like gives it out. What does it mean to optimize something? Like to find the max or the mean. Like usually that's what like how the word is used. So here, like if you're trying to sell stuff, you're trying to make money. So in this case, it does make sense to make as much money as possible. So like I'll kind of think of this problem as like a maximization problem. Like I'm going to find, like my question is, what's the most I can make? Like the most amount of money I can make. So how much of each of I mean, if you want to make it a bit more specific, like it's like asking how many potato seeds and carrot seeds, like how should you should distribute those to make as much as money as possible. Because like the idea, maybe I didn't say it explicitly, but the idea is like since you only have 5 tons of fertilizer, you can grow as much the most you can grow is 5 tons of seeds, like whatever combination of carrots and potatoes that you want. So like that's kind of like the bound. You cannot go beyond 5 tons, because 3 plus 4 is 7, right? Like, so you would, in principle, if you had like 7 tons of fertilizer, then you could just grow everything, right? But you just have to make a decision here. So, and you grow to maximize your profit. And what I like about this problem is that it is such a simple problem that you can already give the answer if you think about it for like 2 seconds. Because if the way I'm setting it up, we know that carrots give you more money, right, than potatoes. So you would like to produce as many carrots as you can, right? So since you have like 4 tons worth of carrot seeds, you would want to use like 4 tons of the fertilizer all going into the carrots, and then the rest you would go allocate to the potatoes, right? That kind of makes sense because again, the problem is simple enough. So it's kind of like nice to start with a problem for which you already know the answer, because then you can reinterpret everything in a more like abstract way and see what's going on. But like kind of like the answer seems to be, 4 tons, like, use 4 tons of the fertilizer for like the 4 tons of carrots, and then like 1 ton of the fertilizer for like 1 ton of like of potato seeds. So like the answer. And so that should give you, like that would give you like, how much would you get paid here? Like you would get paid 1.7 for carrots, so 1.7 times 4,000, because tons, like 1 ton is like 1,000 kilograms. And here you would get paid like, $1.2 for times 1,000. And I think I had done that, if I'm not mistaken. That should give you $8,000. Okay. So in principle, like it sounds like, that is where we're headed. Okay, that's what you would like to say that should the answer be, and we'll kind of like check that by like for like more interesting interpretation of what's going on. But is that making sense? Is like plausible? Everyone kind of like agree with that? Okay, so now comes like the interesting part, and this is where like the linear optimization setup starts like appearing, which is like, okay, let's just actually try to solve this like without cheating, like like just without thinking too ahead of time. So if you are kind of more like cautious, you would say, okay, I don't know how many potato seeds and carrot seeds I want to sell, so let's just call that X and Y, right? Like that's where algebra kicks in. Um, so here's like a more like general solution, right? Like that's how we would like to do this. So let's go like X, like the amount of potato seeds you want to grow. And Y, the amount of carrot seeds you want to grow. Okay. Oops, sorry, let me go. So again, what are we, like this is like in that like like again this could be for like 1,000, 2,000, 3,000, 4,000, 5,000 kilograms, whatever it ends up being. So as I was saying, like let's say in kilograms, just to put some units. So really what we want to maximize, right? We wanted to maximize the total amount you would get paid. The total amount, was $1.2 for potatoes, $1.7 for carrots, right? So like the maximum you want to maximize. So the goal, like let's put it as like a goal. So you want to maximize, I'll obviously drop the dollar symbol. So I'll just put 1.2 times X, 1 plus 1.7 times Y. Okay. Is that okay? That's what you want to make the largest amount possible. And already here, like, this looks like a very simple expression, but already here, there's some linear algebra hidden that you can kind of like disentangle. So because what's going on here? You're multiplying two numbers, and then you're adding them together. So in linear algebra, there's an operation for adding bunch of products, and that's called the dot product, if you remember it. So this is secretly like a dot product, and that actually is like useful information. Like, and you'll see why in a moment. So, so this is actually a dot product of what? Of 1.2 comma 1.7 dot x comma y. Okay, because again, like I don't know if you remember how hopefully I mean as the course progresses, like whenever something is needed from linear algebra, I'll just kind of like review it rather than having like an entire week just to review linear algebra because like there are certain things we won't use until later. So it doesn't make sense to kind of like go like through a crash course of linear algebra at the beginning. I find that like too exhausting. But so if you remember how that product is supposed to work, you multiply the first entry together, then you multiply the second entries together of the vectors, and then you add them up. Okay. Um, so like the function that you want to maximize is actually a dot product. And in fact, all the problems in this course will be finding the max or mean of dot products. Like everything can always be expressed, like all the things that we will do can always be expressed as a dot product. And that's where the word linear comes in, because that means that every variable is just raised to the power 1. So like, let me write that as a remark. So for this class, we want to find the max or mean of things like the general way in which you would write this is like C1 x1 plus C2 x2 plus C3 x3 plus blah 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 Cn xn. And so this you could always write as a dot product between C1, C2, C3 up to Cn dot x1, x2, boom, 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 up to xn. So every single problem that we will deal with in this course is always like a max or min problem for something like this. That's where the the linearity comes from, because none of the variables is being raised to any powers. It's just x1 to the 1, x2 to the 1, x3 to the 1, etc., etc. Which, if you think about it, many times that is just like the natural thing for most variables that you work with in the real world. So, if x is kind of like, again, the number of seeds that you're producing, it doesn't make sense to square the number of seeds. Like, not necessarily. It doesn't have like an obvious interpretation. It's what is like an orange squared or an apple squared? As a mathematical operation, you can do them, but like most of the times they don't really have like a concrete physical meaning. So most of the variables, for most like applied problems, actually kind of like appear linearly most of the time. So it's not like you'll see it's not like a bad assumption to make. But what I'm trying to say is that kind of like the setting that we will work with is like dot products secretly. Again, here is like kind of expanded out very concretely, but more in general, it would be something like this. Of course, in practice, because we don't work with computers per se in this class, usually all the problems will have maybe 2, 3, or 4 variable stops, but like a realistic linear optimization problem could have 30,000 variables or 100,000 variables, again, there are all these network problems of you're trying to ship like your Amazon, you're trying to ship products from one from the your storage storage units to like supermarkets, and then you have to minimize like the total amount of cost, like in transportation problems, and things like that. So there will be a gigantic number of variables involved, but it's all linear basically. Okay, so okay, so that's the first thing, that we're trying to find a max in this case of like this particular expression. And of course, as you kind of like make sense, if you just tell someone now let's ignore the problem, like the original problem. If you just tell someone maximize this quantity, well, you just keep making x and y larger and larger, and that would get bigger and bigger, right? So that's not like that's not like an interesting problem. What makes this problem interesting is that there were constraints, right? Like there were conditions on what x and y could be, and that is what makes the problem like interesting. So let's just think about that. So like it really all the problems we will work with are not just like max problems or min problems. They're subject to constraints. So I don't know if anyone has taken like multivariable. Like I'll just throw this in. This is like kind of like similar to a Lagrange multiplier problem. This is like actually this is why it's very related to it. But like if you don't know what that means, don't worry. Like not something like we will use explicitly. Okay, but like any realistic problem in the real world has constraints. So they're subject to constraints. So they're kind of like some that are obvious, and you don't really think about them too much. But one is, for example, you cannot have like a negative amount of seeds of either potato seeds or carrot seeds. So like the variables are all non-negative. And again, for most like real world problems, that is kind of like a reasonable assumption, like from like an economics perspective, like if you think about like producing stuff. So those are kind of like more like straightforward problems, right? Again, this is like, remember, like this was like the amount of potatoes that we were going to grow, of potato seeds we were going to grow, and this was like the amount of carrot seeds we were going to grow. So if you go back to the original problem that I told you, like I said, oh, you have 3 tons of potato seeds and 4 tons of carrot seeds. You're just trying to determine how many of those seeds you're going to grow. So another constraint that is kind of like natural here is that x, which is like the number of potato seeds, has to be less or equal to 3,000, because that's the maximum amount that you could grow of them. And likewise for y, again, if you think of remember the tons is like 1,000 kilograms, the other one has to be at most 4,000 tons, right? Or sorry, not 4,000 tons, 4 tons, which are 4,000 kilograms. Okay, so those are two other constraints. So far, so good. And the last one that is in the problem, it kind of like explicitly specifies that, you know, you had like you had 5 tons of fertilizer. So that is the maximum amount of fertilizer you could use. So that is like that kind of like gives you a constraint of the maximum amount of seeds you could produce. So like X plus Y, right? Um, actually I use like different, let me, and then X plus Y, you know, that is like the number of like potato and carrot seeds that you want to grow. The most that could be is 5,000 ton, like 5,000 kilograms, because again, you only had 5 tons of fertilizer. So like that's the most like you could grow in this case. Is that okay? Is that making sense? So far, so good. Everyone with me. Okay, and that like makes up like again, if you just think about this problem algebraically, right? Then you can kind of like draw it. So okay, it makes sense to draw this on the XY plane to draw the inequalities. So let's try to draw this. Okay, so what do the first two inequalities tell me? They just tell me that like X has to be non-negative and Y has to be non-negative. That's another way of saying that you're working in the first quadrant. So that's great. Like, you know, that just means like whatever you draw, you just have to focus on the first quadrant. So, and in most problems, like again, realistic problems that we will work with, like the variables are naturally non-negative. That's kind of like the basic assumption we'll make most of the time. So, uh, so that means that we are dealing with the first quadrant. So it doesn't really matter what happens after, like outside the first quadrant. Okay. So that is where we're trying to find the max inside the first quadrant. Like we don't care, like we wouldn't want like a max that gives you a negative value for like the number of seats, for example. That would be silly. Okay. So what is like x equals less or equal to 3,000? Like, you know, well, you have 3,000 here. And you're looking at all the points, right? Less like where the x value is less or equal to that. So like x equals 3,000 is like a horizontal line, right? Actually, probably we'll put like each inequality separately, and then we will take like the intersection, like so that it looks like a little bit more clean. So again, you're looking at everything on this side, but you don't care about like the non-negative stuff. Like you only care about the stuff in the first quadrant. So like I'll just color the stuff that this inequality corresponds to in the first quadrant. Okay. Again, we only care about the first quadrant. Then again, like you could put all of them at once on the same picture, but it's kind of like better like to do them separately, at least like the first time you do this. And then y has to be less or equal to 4,000. So again, here you would have 4,000. So y less or equal to 4,000 is all of this a kind of strip, but I only cared about the stuff in the first quadrant. So I will just color this part. Uh, So far, so good. Everyone with me? And last but not least, actually, this is kind of like the more interesting one, right? X plus Y has to be X plus Y has to be less or equal to 5,000. So I don't know if you remember how you would plot something like this. Like, you know, you can plot the equality first. What is the equality? It's like X plus Y equals 5,000. So that is like a line, right? Like that's 5,000 minus X, right? So like this value would be 5,000, this value would be 5,000 also. It's kind of like symmetric. And then like the line divides the plane into two regions, and only one of the regions satisfies the inequality. How do you check? You just do it by like, you know, like the origin satisfies the inequality. 0 plus 0 is less than 5,000. So like this side is like the one that works. And again, in principle, you would color the entire side, but you only care about like the stuff inside the first quadrant. So I'll just color the triangle basically. Again, we only care about the like first quadrant. So these, so far so good. So these are like each inequality like separately, right? Like this is like where you have to be to satisfy the first inequality. This is where you have to be to satisfy the second inequality. And this is where you have to be to satisfy the third inequality. But you want to satisfy them simultaneously, right? So you want to kind of like look at what you would call like the intersection of the three regions. So the easiest way to like, what are the relevant values here? Like they are like 3,000, 4,000, 5,000. So like you just plot, like put that all into this. So like I would have 4,000 here, 5,000 here, you know. Then I also have 3,000 here. And then I would have 5,000 here. Okay, and so the region, like if you kind of think about how this is supposed to look uh, and in fact, actually probably drawing the lines is also convenient. So I'll draw at least like the part of the lines that is relevant to the picture at hand. Oh, well, this is how this would look like. Oh my God, let me see if I can, should I draw them? This is where like drawing it to scale would be better, actually. Okay, so yeah, I don't want to make them look like they all meet like kind of like the same point. That's what I'm trying to avoid. Maybe this looks better now. I think it will. Okay. Oh, okay. The thing is like, right. Like this point, oops. The problem was like with these pictures, like this point of intersection actually happens like above these. How should I fix this? Oh, okay. I'll fix it this way. Sorry. Like you can already see that this is like a thing where you have to be careful what you do. Uh, like even this, like because of what happened. Like sorry, just to explain what happened. Like this point where this meet is 3,000 comma 4,000, which is above the green line. So I wanted to reflect that accurately into the picture, because otherwise it would come wrong. So uh, you know. Like 3,000, 4,000 is above the green line because like it adds up to more than 5,000. So if I had put like like you don't have to do it to scale, but you do have to be careful because if I put it like originally where it was here, it kind of looks at that point is below the green line and it's not. So like even like a simple toy model like this, like you cannot draw something crazy because otherwise it is misleading. So you have to be below blue, to left of red, and below green. So if you color those three things, like it's not too hard to color them. Uh, you get something like this. So this is a region that satisfies all the inequalities simultaneously. Okay. In fact, let me kind of like zoom in a little bit, like make it a little bit bigger, just to like emphasize some certain features. So it kind of like just to make the colors. So this is how the region looks like. This is like what in the like just to give you some like of the terminology that we'll use later. This is what like in linear programming is called like the feasible region because this is like potentially where the max could be. Like, so this is like the allowed region. Like, so this is called like the, well, but like the name that people give to this is like the feasible region. And this, I mean, like that's not a name that you have to worry about for now. But this is what you call like a polyhedron. Like that doesn't matter too much right now, but I'll just throw in the name. And all the regions, if you were to draw them, are always polyhedra. Like that's also like an important thing. Like the reason why that's important is because these are convex sets, which I'll tell you what that is later on. But convexity is one of like the key properties like in optimization, like for things to work well. So, but again, like I'm like just um throwing now like a bunch of words that they don't matter too much right now. Like the important thing is that you have like this kind of like funny region. It's like a like in a sense, like I guess it's some sort of polygon in this case. Um, but the cool thing is like it has corners, right? So you can see the corners here, like this corner, this corner, this corner, this corner, and this corner, right? Like this one has what, 5 corners? And one of the key results of linear optimization is that the max or the mean can only occur at the corners of the region. That's like impressed. Like, and we should go over that like at some point, but uh one of the key facts, and it's not specific to this problem, is always true. The max or the mean can only occur at a corner of the region. Can only occur at one of the corners. Is that okay? And of course, like there's like an explanation for that. Like I don't think it kind of makes maybe a lot of sense to kind of like get drag into it right now. Although I'll show you like a cute animation I made about it in a moment. But it is basically because the function is linear. Like in, there are many different ways to do like explain it. Actually the dot product kind of helps, but I'll write some like, probably next time I'll give you like a bit more like of an idea for why that happens. But these, like, once you know that, uh, again, if you don't know anything about the problem, this kind of reduces it to a finite question, right? Because you have a finite list, 5 points, right? So, what are these points? They're 0, 0, 3,000, 0, 4,000. Sorry, 0, 4,000. Sorry, my other tablet died. I like have to resurrect it. Then this other one is 3,000, 2,000, and this last one is 1,000, 4,000. Okay, so you have 5 points to look at. You have to make a table with 5 points and determine which one gives you the max. So like you would just make the table. It was like here's the value for x, y. Here's like the function. What was the function? It was like 1.2x plus 1.7y. Okay. And like, okay, this is like not too bad to like do like 0, 0 clearly gives you 0. That's good. 3,000, 0 gives you 3,600. Then like you can do the easy ones first, where one of like the variables is entry is 0. So like 0, 4,000 gives you 4,800. And then 1,000, 4,000 gives you 8,000. And then 3,000, 2,000. Close, but not the same. Gives you 7,000, 8,000. So sorry, it gives you 7,000. So of course, like of this list, like the winner, right, like the max, because you were trying to make as much profit as possible, would be this one, which we already knew even before we did anything. Like that should have been the answer, right? Like because if you just think about it for a second, that was like the answer. So like this is where the max should occur. this point. But like again, and I'm still not done with this example. There's still some like useful things you can extract from it. But already there are a few things that this is saying. Like the first thing is like that is saying is like like the max or the mean that we will deal with are always dot product. Again, that will be useful later on. They can always be written as dot products or like they're linear, meaning like every variable is just like raised to the power one. That will always happen. We will always have constraints or inequalities that need to be satisfied. This kind of like two more or less will always be true. And these are like the ones that are more like vary from problem to problem. And then if you put like the constraints together, you kind of get like some like funny looking region with corners and like the maximum appears at one of the corners. Okay, so all of those things are more or less true for every single problem we'll do in this course. Okay. Um, before kind of it's sorry.
Oh, is there any differences between this and budget constraints and utility functions?
I mean, like a budget constraint, I mean, like you can kind of set it up in this same way. Like, there are a few different ways to set up like these problems, which we'll go over. So for example, I wrote like the constraints, all with inequalities. There's like a trick you can do to write them as equalities, which is called like adding like slack variables or surplus variables. So there are different ways to set it up, but yeah, like that budget stuff, like, would follow like, it's kind of like one of the basic examples of like linear optimization. Of course, like realistic budget problems like will be like gigantic, right? Which none of which is this like at the moment, but this actually, it's like a cute, like simple enough problem, but it does kind of like show you like the general features of what happens, even if there were like 100,000 variables involved, which is kind of like why I want to kind of like go into a lot of detail with this one. So far, so good. In fact, something that will be just to go back to the constraints, again, like just like notation wise, because like that may be useful for something I'll mention like in a bit. Um, as I said, like most of the time, these are kind of already baked in, so you don't think of them. I mean, they will always be written down, but they're not kind of like too interesting of constraints for us because they're more or less always true in every single problem. So more or less in every single problem, the variables will be non-negative. So they're kind of like less important. Like the last three are kind of like the more like variables, like in the sense like they change from problem to problem. So if you just focus on those three, let me copy paste them. So like let's call them like the interesting constraints, like not just to like be demeaning or anything, but like like they're kind of like the ones that are like genuinely like like as specific to a problem. So like if you look at this in like more like interesting constraints, again, like there's a reason why linear algebra is a requisite. So there a bit of an overkill at this point, but you can rewrite this using matrix notation. So you have if you thought about this as equalities, you would have three equations and two variables, 3 times 2. So you should have like a 3 by 2 matrix. Like, if you just think about like in terms of like equalities, not like inequalities. So you should have like a 3 by 2 matrix. In fact, like the easiest way to find this is like just put equals, equals, equals here and set up like the matrix equation, and then you put like an inequality at the end. So, so how do you read off the coefficients? They're just like the numbers in front of like the variable. So it's 1, 0, right? Then 0, 1, and then 1, 1, right? And if you do like, I don't know if you remember, like, maybe again, I just want to do this like for matrix multiplic, this is like a 3 by 2 matrix, right? This is like a 2 by 1, well, it's a vector, but it's like a 2 by 1 matrix, right? The condition for doing matrix multiplication was that these two numbers agree, so this is good. That should produce Oh, sorry, I forgot the 5,000 actually. That's actually why matrix like actually going through like these numbers like help you, because this should produce a 3 by 1 thing. So that tells me, oh, I actually forgot something here, which should have been 5,000, right? So coefficients. Uh, so we're almost there. And then how do you read out these numbers? Like, like they're just like the coefficients from the other variables. Like here, there's no y, so it's plus 0y, plus 0x, and then 1, 1. And of course, this is not with equality. It's just like everyone is less or equal to. So just put like less or equal here. That fixes it, the problem. So you interpret this as like an inequality for each of like the entries of the vector that you get. And in this notation, if you call like what is like usual notation in linear algebra for these systems, A, X, B. So if you call this A, this is X, and this is the vector B, like the interesting constraints can always be written like at least like again, there are different ways to write them. But like this is kind of like a basic way to do it. Oh my God, constraints. Kind of like you can write them as A times X is less or equal to B. Okay. At least for the system I wrote, you know. Again, like next week probably we'll play a little bit of how do you re-express these equations. There's like a very cute trick that always turns this into an equality. You just have to add like extra variables, but like we'll go into that later on. But so you should think about like like just to rewrite things again. So and you see how we're kind of like stepping up like the level of abstraction, because now this is all like in terms of matrices. So really like the problem that we started with was like you wanted the max. So you wanted the max of a dot product, right? Subject to, that's just how you would write it. Like subject means like that it must satisfy like the inequalities. So it must satisfy all those inequalities, which you can summarize very neatly into this like matrix inequality. And the entries of this vector have to be all non-negative, like again, most of the time. So you would also put that x is greater or equal to 0 vector. So like that just means that the way you should read this is like every single entry is greater or equal to 0. Like, it's kind of like an entry by entry inequality whenever you write like the inequality sign between vectors. Okay, that's how we will understand it. So that is kind of like, it started with a simple problem, but this is kind of like more or less like the structure or more of 50% of the problems like that we will do in this class. Like, they will always kind of take this like shape. Um, oh, what I was going to say before, like continuing with this example, is that, and again, like, I'll just put C video because I'll show it to you right now on the GeoGebra, but it's kind of like hard to draw it on. So C video recording if you review the notes. Because it's kind of hard to draw it on the tablet. But like again, we were trying to find the max of 1.2x plus 1.7y. So if you introduce an extra variable, so you're trying to maximize, again, like this is kind of more like a remark. And you may remember this as the equation of a plane. Like the equation of a plane is more or less something like of this form. So this is like a plane in 3 dimensions. Okay. So you're trying to find the highest point on the plane above the region, the constraint region. So let me show you how that looks like, because it took me a few minutes to do, so I do want to share it. Aha. Let's see. Okay, so that is let me see if I can, like, it looks terrible right here. Okay. So there are a bunch of random points. So this is kind of like, you know, the graph of the plane, like it kind of like stands like in all directions, but it's kind of like hard, like GeoGebra will only show you some portion of it. Then you have where are these polygons? Like, no, this is one. Here it is. So this is like the polyhedron or that I had drawn on the XY plane. If you remember it, kind of looks like the same, hopefully. So then you have this function, which is like the plane. So you have a piece of paper kind of like floating above the polyhedron, which is hard to see a little bit here. But that kind of like, so you don't care about the entire plane. You just care about the part that is literally above the polyhedron, and that gives you. That's what I was trying to show. Like, let me see if it looks a bit. It looks better if I delete this other graph. So that gives you this region. So if you like, I don't know why this animation doesn't allow me to kind of like move the axis. Like I'm like, if I had it on my computer, I mean, like, let me see. I do have it. I do have the file on my computer, so I should be able to just like show it. Yeah, because it's terrible not to be able to. No. Oh, yeah. Like open local file. I did it somewhere in here. So optimization, polyhedra. Is this one? Okay, it's like it just looks better here because like I can kind of like do the 3D motion. Like, let me share this again. So what I was saying is that it's kind of cute. So if you have polygon 1, that's like the shadow, right? Like that's on the XY plane. That's all the constraints being satisfied. Like, so if you look at it from completely vertical, like that just looks on the picture on the plane. And then polygon 2, it is literally you kind of like lift this and draw it on the plane, and that is what you get. So you see, like it kind of sits on top of it, like literally. If you can, like the shadow of this one is like the one on the plane. That's what I'm trying to say. But it's kind of like, if you kind of think of the graph as being like a piece of paper, it's kind of like clear why the match for the mean should occur at the corners, because you're trying to get it as far away as you can, and that's kind of like limited by the corners of the region. So in this case, it kind of corresponds to the point H, which kind of it's like, no, I mean, kind of like I think it corresponds to this one. So that would be the highest point. Yeah, you see like H is kind of looks better here. H is the highest point, which sits directly above this one, and that one like 1,000, 4,000, or something like that. So that's kind of why the max are roughly, like one of the explanation for why the max and the mean always occurs like the corners, because like the function is linear. So it has, like if you just imagine like a linear function in more dimensions, like kind of like the same story worked in the same way, but it's like a bit harder to visualize, But it's kind of, yeah, sorry.
Sorry, so that that plane that we just
Mhm.
drew,
I
is
can
that v equals 1.2x plus 1.7?
exactly.
And then
Yes.
we're gonna do the constraints.
Right.
Um,
Yes.
Why is it extending all out to z?
Well, the thing is, like, as a function, like, here when you plot it in GeoGebra,
Yeah.
I'm not telling GeoGebra that X and Y take specific values. So GeoGebra is just plotting it in the entire space. So of course, like, you don't care about all of it, right? You just care about like the part of the plane that's literally above the shadow region, and that is why kind of like I deleted the plane from the picture. Does that make sense?
Yeah.
Yeah. Like when you put it on GeoGebra at the beginning, it would just show you the entire thing, like, which you don't want, right? Like you only want like the stuff that sits like above the region.
Okay, got it. Thanks.
No, good. Perfect. So let me just I think I should have enough time to mention this. So, okay, so this is actually related to something very useful. So this is like the first big idea of the course. Oh, maybe I should, I'm going to totally to forget it, like, so I'll say it now. So in general, you always, what I like to summarize what was happening here. In general, what I was saying is that the max or min can be just found at the corners, right? Um, well, and so you could say like, and which is a finite number, like, like there's only a finite number of corners. So in a sense, you could say, okay, this is completely silly because like, you only have to look at a finite number, at a list of a finite number of problems, so the problem is solved. Yes, for a mathematician, but like the number of corners can grow exponentially, so that messes up your life, right? Because once you have exponential growth, everything goes like, stops working. Like, like you can quickly, like 2 to the 50 or 2 to the 80 is a number larger than the number of atoms in the entire known universe or something insane like that. So like exponential growth is really fast. So the number of corners can grow like exponentially with like the number of variables or like equations. So number of corners can grow exponentially with the number of variables equations. So what that means, like in a nutshell, is that you cannot just go like crazy evaluating all the corners. Like that is like a waste of energy, a waste of effort. Like it would take you nowhere. So you cannot just like like realistically, you cannot just like evaluate one of every single corner. For like real like interesting problems. Of course, for all of these you could, but like you should think that you want to work with a problem that has thousands of variables or thousands of constraints, not like a baby problem, right? Like like an actual problem that you would work with. So realistically, you cannot evaluate all the corners. Mistakenly. Okay. So what the simplex method will do, and that's kind of like the main insight of the course, like or like the main insight of the algorithm. Oh, sorry, like I always forget that this kind of goes down. Like the simplex method, the way, and I kind of will explain that in a couple of weeks once we kind of deep dive into it. But the idea of the simplex method is kind of like how to kind of like, it's kind of like a search algorithm. So it's how do you efficiently navigate the corners of like the region to find the max. So it's kind of like a strategic like search method for like finding the correct corner. So I'll just leave it at that because I have to give you more like details next time. So it's like kind of like a search method to find the correct corner. Okay. And again, this is kind of like the analog of like Gauss-Jordan elimination of matrices. So this is kind of like the bread and butter of the course. Like this is more or less whenever you want to solve like a linear optimization problem, this is what we will use. There's another technique which is kind of like cool, which I'll mention like later on, which is like Fourier elimination of like Fourier-Motzkin. I don't remember like the second name, elimination of variables. It's actually very like theoretically, but like in practice, like this is what the people would use. And then just maybe to wrap this up for today, and I'll kind of like continue this like next time because there's something like also something interesting in this problem, which is kind of like hidden. Let me see, like again, I'll just kind of give like a brief explanation of it, and then like I'll return to it next time. Okay, so just back to like the constraints that we had, like at this point, it's kind of like better to kind of like name them differently. So I'll just call them x1, x2, just to be a bit more consistent. Oh, okay. So you have three inequalities, right? And now you can think about it as a game, and you had to maximize what is like the goal? To maximize 1.2x1 plus 1.7x2. So I won't give you the answer today because like I don't have enough time, and also like that way it gives you like a chance to think about it for your own if you want to kind of think about this. I'll probably write it as a Canvas announcement just to remind you to consider this. But like again, imagine you don't want to do any pictures, you just want to play algebraically, you don't want to draw anything. Like you don't want to draw the corners, like, or you find that too hard. So you could try to say, oh, can I just play with these inequalities to kind of like determine this, like the max, like directly from the inequalities. So for example, here's one thing you could do. Oh, let me call like maybe the inequalities like ABC so that because I want to use numbers, so I don't want to kind of like bias this a lot, you know. So here's like an example. Imagine you wanted to do, I want to like, I don't know, maybe if this will make more sense once I kind of like write it down. But I want to work with this inequality to see if I can give like a direct bound for this. So for example, 1.2 appears like multiplying x1. So what I could do is like multiply this the first inequality by 1.2. So I could do 1.2 of inequality A, right? Plus, like you can add in like everything is kind of like positive coefficient. So like you can just add directly like the inequalities. And like x2 is multiplied by 1.7, right? So you can multiply both sides of this inequality by 1.7, right? So what this means is like multiply both sides of A by 1.2, multiply both sides of the inequality B by 1.7. So I'll kind of like write it like here. So if you want. Right, if you multiply both sides of like B by 1.7, what was like, oh my God, like now I don't remember what is 1.7 times 4,000. I think, it is like what, what is 1.7 times 4,000? 6,800? Okay. I promise to use very simple numbers. So, okay, so like this is like how each of the individual inequalities would look like, right? And if you add them, like you just add up the left-hand sides, add up the right-hand sides. So that would give you that 1.2 x1 plus 1.7 x2 is less or equal to, that is 10,400. Is that kind of like making sense what I did? So like I kind of like, I had this coefficient with 1.2, I had this coefficient with 1.7. I use the first two inequalities multiplied by the appropriate coefficient, and that tells me automatically without solving anything that the max, whatever it is, it cannot be higher than 10,400. Is that okay? Is that making sense? Of course, like that is like a very bad inequality because we kind of already know that the max had to be at 8,000. So this is kind of like, giving like a large gap. But what's kind of like cute about doing it this way is that you only, you only play directly with the inequalities. Now you could ask, can I do better? Right? That's kind of like the interesting question. Like, and I kind of like finish it like here. So here's something like you can notice, like when I kind of combine the inequalities, I kind of like ignored like the last one completely. So maybe like you should incorporate this somehow. So how could I incorporate the three inequalities? I could do, so let's think of 1.2 as 1 plus 0.2. So I'll do 0.2 of inequality A plus, what is 1.7? 1.7 is 1 plus 0.7. So I'll do 0.7 of inequality B, and then I'll do 1 of inequality of inequality C. So what is happening here, that would says that 0 point, and I'm almost done. That says that 0.2 would be less or equal to what? 0.2 times 3,000. That's 0.7 of x2 is less or equal to what? 0.7 times 3,000. And the last one, it is that would give you that x1 plus x2 is less or equal, sorry, x1 plus x2 is less or equal to 5,000. So I don't know if you see what I'm trying to do. But the idea is like, for the function, like the coefficient of x1 had to be 1.2. So I'm just breaking 1.2 as 0.2 plus 1. Sorry, 0.2 plus 1 would give you 1.2. And then 0.7 plus 1 would also give you 1.7. So if you add up the numbers here this way, that would give you that if you add up the inequalities, that would give you that 1.2 x1 plus 1.7 x2. That actually gives you 8,400. Okay, if you kind of like do all the products. Okay, so this is like a lot better, right, than the previous inequality. So the question is, can you actually get to the value 8,000, right? Could we play with the coefficients in a strategic way so that we get to 8,000 as like the bound here? And the answer is that you can, and that's actually called like the duality theorem. And like I'll probably mention some of those things like next time. But like for you to think about it, like I'll just leave it as a challenge. So challenge for you to think if you want over the weekend. And that is solving one of the important things. Like, can you choose coefficients? Choose like coefficients. Y1, let's call them Y1, Y2, Y3, so that if you do Y1 of A plus Y2 of B plus Y3 of C like I just mean like inequality A, inequality B, and inequality C. Can you choose like the numbers here strategically that would give you 8,000 as the answer? And if you do, that is kind of like would have been like the best way to play with the inequalities to find the max. And so again, I'll kind of go into more details like next time, but I just wanted to leave you something to think about over the weekend. So I'll write it like I'll probably write it in a more like precise way for you because I kind of went a bit fast over this like right now. And the answer is that you can, and that's actually called like the strong duality theorem. So answer you can. And this is related to something called duality. And you'll see why duality appears here because there's like that transpose of the matrix A from last time. Yeah, let's end here, by the way.
Are we gonna go over like this in more detail?
Yeah, I'll kind of finish it like on Monday.
Oh, okay, that's
Yeah.
good. Thank you.
Sure.
I have a question.
Mhm.
So right here, we're looking at, like, so we had, this was like Z, right?
Correct, right.
And so when we include like all of the constraints, we somehow get like it's less than or equal to.
Correct. It is,
So where is it equal to? Because the highest point is 8,000, right?
right. So the thing is, like, I'm playing like the way you should think about this is like I have three inequalities, right?
Yeah,
And I'm trying to play with the numbers that I put in front of each inequality
yeah.
so that I get to 1.2 and 1.7, right? So I kind of did two obvious ways, which were like, 1.2 of the first one and 1.7 of the second.
Yeah.
Another way you could have combined them, right? It was like 0.2 of, the first one plus 0.7 of the second one plus 1 of the third.
Yeah.
But there are other ways to combine the inequalities. This is not the only two ways to do it. So there is another way to combine the three inequalities that will give you 8,000. And that's kind of like the challenge if you want to think about it over the weekend. Yeah, but I'll kind of go over it during class on Monday and let's say how you would find the answer.
Okay.
But like, like kind of like the idea is like, who told you that these were like kind of like the two only ways to play with the three inequalities? There are other ways. And one of those ways does give you 8,000.
So we're combining the three inequalities,
Correct.
but we wanna have this equation, right? So
We kind of
this is C,
right, because this is right. Like it wouldn't make too much interest if you somehow got to like, 7x1 plus 8x2, because
Okay.
how is that related to the original problem? You know what I mean?
I see.
Yeah. But
Okay.
it's kind of like a game. I'll kind of write it down, like if someone wants to think about it over the weekend, but it's kind of like a fun combinatorial, like it's kind of like a trial and error problem.
Okay, got
But
it.
like, there's kind of like a more like elegant solution, which I'll discuss on Monday.
Okay, thank you, Professor.
Sure.
Have a nice day.
I had two questions.
Uh-huh.
So one question I had was, are you gonna post the notes online?
Yeah.
Okay, and then the second question I had is there gonna be any proofs in this class?
Uh,